In this video, I'll be going over the different ways that we can solve exponential equations. So here are some examples of exponential equations. What we'll notice is that we always have at least one exponential expression. So this equation has two, as does this. This third equation only has one exponential expression. So there's different strategies we want to follow depending on the format of the equation. So the first way we want to go about this is by getting the exponential equation to have like bases for the exponential terms. So for example, if we have 5 to the 2x is equal to 5 raised to the 3x plus 2. Because these bases are the same and these two expressions are equal to each other, what that means is these exponents must also be equal to each other. So when the bases are the same like this, they're both 5, what we can do is simply set the exponents equal to each other and solve. So x would be equal to -2 here. Now that's about as easy as it gets. We won't always have bases that are already the exact same. Sometimes we will need to rewrite the base in order to get it to be the same. So in this second equation, 256 is equal to 4 raised to the x minus 5. What we want to do is rewrite 256 as 4 to the 4th power. Okay, 4 to the 4th is 256. So now that the bases are the same, we can simply set the exponents equal to each other. 4 is equal to x minus 5. X is going to be equal to 9 here. Let's look at one more. Suppose we had 5 raised to the 4x is equal to square root of 5. Well, really, the square root of 5 is the same as 5 to the 1/2 power. So these bases are actually the same. So 4x is equal to 1/2. So x is going to be equal to 1/8. So that summarizes the first type of exponential equation we'll have, and that's when we can write the bases the same. The next way to solve an exponential equation is by using logarithms. Now, there are two different ways we can use logarithms. The first way we could do this is by taking the log of both sides of the equation. The second way is to rewrite as a log equation. Now we can do either of these methods with any exponential equation. However, it makes the most sense to take the logs of both sides when we have two exponential terms or an exponential term on each side. So actually, let me write that more precisely. Okay, so when we have an exponential term equal to an exponential term, that's when it makes sense to take the log of both sides. And we will most often rewrite as a log equation when we have one exponential equal to a constant, or more precisely, let's say, not just a constant, but some other type of polynomial expression. So that could be a constant like a number, or it could be something linear like 3x plus 2, etc. So we'll see both examples here. So let's use logs to solve this equation. 2 raised to the x power is equal to 3 raised to the x plus 1. All right, so in this one, this is going to fall into category A here because we have an exponential equal to an exponential. So we'll take the log of both sides here. So what we're going to do is log of 2 raised to the x is equal to log of 3 to the x plus 1. All right, so at this point I'm going to apply some of the properties of logarithms to try to isolate the x. So on the left-hand side, we use the power rule to rewrite this as x log of 2. And then over here, I'm going to use the power rule to rewrite this as x plus 1 log of 3. Now it's really important that x plus 1, that whole thing comes down and we write x plus 1 in parentheses. Now on the right-hand side, I'm going to distribute the log of 3 term through, so x times log of 3 plus 1 times log of 3. We don't even really need to write the 1 there. And on the left side, we still have x log of 2. Okay, so we have 2 terms that have x's, so I'm going to gather all the x terms on the left-hand side. So I'm going to subtract this. And then when I want to isolate the x out of 2 terms like this, I'm going to factor. So x factors out log of 2 minus log of 3 is equal to log of 3. And then lastly, we're going to divide both sides by log of 2 minus log of 3. So what we end up with is x is equal to log of 3 divided by log of 2 minus log of 3. And that is our solution. So this doesn't really make a ton of sense to us because I can't really, maybe you can, but I can't come up with decimal approximations of that expression. So I'm going to type this into the calculator. And we need to be very careful and use lots of parentheses to make sure that what we're entering is representing what we want. And what we get here is about negative 2.7095. Okay, so what we would say is this is an approximate solution, and this ugly looking fraction is the exact solution. So most of the time we want to know what the exact solution is, so we don't need a calculator to find that. So let's actually graph both sides of this equation and see if that confirms what we got as our approximate solution. So on Desmos here, I graphed the left side 2 to the x, that is this red graph, and then the blue graph is 3 to the x plus 1. What we notice is that they intersect at this point. So the blue graph, I want to say bluegrass, the blue graph is below the red graph here, and then it hits the red graph and is then above the red graph. So this point, or this value, negative 2.71, is the x value that we found as our approximate solution. So the graph confirms what we got as the answer. All right, let's use logs to solve this exponential equation. Now this exponential equation only has a single exponential expression. When we have that situation, we convert this into a log equation. So if we go back to what we had down here, this is the situation we're going to use because we have an exponential equal to a polynomial. All right, so I'm going to isolate the exponential expression first. So I'm going to divide both sides by 2. So 29 over 2. Now I'm going to convert this into a log equation. So remember, logs equal exponents, so the exponent is off by itself. The base is 10, and then 29 over 2 is 14.5. Okay, and then the last thing we'll need to do is divide both sides by 9. So what we end up with is log base 10, which I could just write as log 14.5 divided by 9 is the exact solution, and that is equal to A. And then if we type that into the calculator, for an approximate solution, I end up with about 0.1290 as the approximate solution. Okay, so 0.13 about is the value for A that solves this equation. All right, next example here. This is a similar situation as the previous example. We're going to isolate the log expression, which is this. I'm going to add 4 to both sides, and then divide by 8. So we get e to the negative 5x minus 2 is equal to negative 86 over 8. All right, we have the exponential expression isolated. I'm going to take the log of both sides. Logs equal exponents, so the exponent is off by itself. The base is e, so we're going to say ln, because remember, log base e is the same as ln. So ln of negative 86 over 8. Okay, so then what I'm going to do is I'm going to add 2 to both sides and divide by negative 5. So we end up with ln of negative 86 over 8 plus 2. The 2 does not go inside the argument of the logarithm. Only negative 86 over 8 is inside the logarithm. And we're going to divide everything by negative 5, and that will give us x. So that is our exact solution. All right, let's use logs to solve this exponential equation. Again, let's isolate the exponential expression. One common thing, or one common mistake that students will make is they won't isolate this first. Okay, if we don't isolate that exponential expression, we're not going to be able to solve this. In other words, we're not going to be able to easily convert this to a log equation. So the first thing we want to do is divide by both sides by 20. 100 divided by 20 is 5. Okay, so now we have the log, or the exponential expression isolated. So let's convert this to a logarithm. Logs equal exponents, so the exponent is going to be by itself. The base is e, so we use ln of 5. So t is equal to ln of 5 all over 2. Another common mistake is students, when they divide both sides by 2, they write this, ln of 5 halves, and that's not what we want to do. Okay, it's kind of like if we had this, 2x is equal to square root of 5. When we divide both sides by 2, we don't write square root of 5 halves. We write x is equal to the square root of 5 all over 2. All right, so those are just some tips for us, and this is the exact answer. This last equation is a little bit different than the previous ones. E to the 2x minus e to the x is equal to 56. What you may notice is that this looks close to a quadratic equation. That would be in this form. So when we want to solve this exponential equation, what we can do is we can try to factor it. So if we had the regular quadratic equation, we'd set this equal to 0, and then we'd factor like this. We'd get x is equal to 8, x is equal to negative 7. So we can try something similar here. We're going to set this equal to 0. And this one's going to factor as e to the x in the first position, and then minus 8 plus 7. So when we multiply e to the x times e to the x, we add the x's, x plus x, so that's why we end up with 2x. So from there, we just set each equation equal to 0 and solve. So we get e to the x is equal to 8. E to the x is equal to negative 7. Okay, so now these are simple exponential equations. I'm going to convert this into a log expression, or a log equation. The base is e, so this will be ln logs equal exponents, so this is just ln of 8 is equal to x, and then this one on the right is going to be ln of negative 7 is equal to x, but we can never take the logarithm of a negative value, so that is not going to be one of the solutions. So the only solution is ln of 8. And as an approximate solution, we get about 2.079. All right, so that's it for solving exponential equations.